Next up, we've got Phil Hagerty with AGC Chemicals.
Thanks for having me. Can you guys all hear me? This is good volume. Thanks for having me. I'm Phil Hagerty with AGC Chemicals. We're a large global chemical company, and one of the product lines that we have is Lumiflon, an FEV resin, which we are seeing continued interest in the corrosion space. So today it's fluoropolymer coatings, corrosion resistance for bridges. We'll go through an outline real quickly of what we'll talk through. So we make the fluoropolymer, the FEVE coating, and we'll talk through conventional corrosion testing, some of the weatherability that we have, and then go into some of the EIS, Electrochemical Impedance Spectroscopy, that we've looked at and we've seen within our resins for some top coat formulations that we've had, and then get into some of the life cycle cost analysis. And this is within the steel portion of when you're looking at bridges. So you use it in the conventional three-part system for when you're looking at your bridges. And then after that, we'll go through some case studies. I want to quickly go through this because not everyone needs chemistry, high school history, but essentially it's a copolymer. So it's a fluoroethyl and a vinyl ether. So they're done in a polymerization reaction, and the reason that they're done in that way is that it gives you the benefits of a fluoropolymer, but also you can cross-link this with the vinyl ether. So that's going to give you the nice gloss, the nice solubility, and within your paint formulation, but it's also going to have that nice chemistry of the fluorine, where it's going to give you that weatherability, that durability. Nothing's going to break it down, and that's partly the chemical and then the corrosion. So just to go through some of the properties, I mean, there's certainly a lot. There's certainly a lot to be taken advantage of within. You're looking at this chemistry set, but you're looking at a coating that gets you 30 plus years. And we can confidently say that because we've seen that within the field, especially within Japan, where they've used these coatings, and that was the main reason they were invented. We give ourselves a hard time. I've seen it at a couple discussions within the US about bridge preservation, getting from poor to medium to good. But we actually do a good job globally if you look at ourselves compared to some of the international standards. And they invented this material specifically for steel coatings to get 30 and 60 years because they can't shut down a bridge in Japan. I mean, it's an island country, so they've written it into what they look at, and they use this in all their steel structure coatings. It can be shop or field applied, new construction, or even on maintenance. So if you want to start fresh, but the reality is we're all looking at preservation, you can use this as a preservation coating as long as you do your surface prep correctly. And you're going to get that resistance to weatherability, you're going to get that chalking resistance, that resistance to chemicals that you use for a lot of the salts that you're using. I know it's less important here, but for some of the coastal environments within the salty environments. So I'll touch base just to give you the weathering. I mean, this is the backbone of why it was invented, was the weathering resistance. The corrosion is something that's really come about and new in some of the demand from the industry. So if you're looking at it compared to a polystyrene or an acrylic resin, you're really going to see that gloss retention. And this is accelerated weathering. This isn't out in the field. So it's an indicative. It's not going to be an exact one-to-one comparison of what the real world's like. But this just shows that we've done over 12,000 hours of testing for UV exposure. And we've also done the real world in South Florida and done exposure, and we've compared this and what gloss retention you're going to get after 10 years of exposure. Ideally, we'd want to go beyond 10 years and would love to present that data, but our panels got blown away. It's South Florida, so it's inherently going to have some weather there. But this just gives you the proof that we've done some of the testing on our products. We've done some of the chalking resistance. We have this data. Happy to present on any further or talk further with our chemistry team or on our labs if you guys have specific questions on what the formulation was, what that looked like. But I really want to get into where we're at with the corrosion, because that's why we're here. It's what most people are interested in. And corrosion is one of the primary reasons why you're going to look at using an FEVE or a Lumiflon based system. And this is you're going to use it in the field with your traditional three-part coating system. This test that we have done that I'll present on next is just with a panel, and I'll show you some photos. But like the top coat prevents that corrosion from even starting. If you have a good top coat, if you have a good first protection layer, then you're not going to necessarily have to worry about what the corrosion method is. As long as nothing gets through that first layer, it's not going to start. Where you're going to have it start is where you have dings or you have other issues, and that's what we've seen within the corrosion, where some of our top coat, you use the Lumephon in the top coat, you're going to see some of that benefit. So this is why corrosion resistance is one of the strong reasons why people are using it. And this is a specific test if you've done this or looked at this, and this is the ASTM B117, and so we took a high performance polysiloxane, and we also took a high performance polyurethane top coat, and we compared them on panels compared to what a Lumephon based FEVE coating system would look like. This is just the top layer. So we scribed that top layer and opened up and said, hey, corrosion, go ahead and start. And this really is testing how good the panel is at resisting. But in what we found from this too is that Lumephon, even though it's scribed, you're opening up to corrosion, you still see a benefit. And it's noticeable if you look at the left panels, which are the ones of the polysiloxane and the polyurethane, and each of the image individually on the right is the FEE based. That really gives us the indication of, hey, corrosion is less when you're using a FEVE top and you have a defect within the surface that's getting to your metal surface layer. So this isn't with the zinc primer. All right. So another test that we looked at is the the SEMD 589-4, the Cyclic Prohesion. And essentially what we're looking at is what was the creep length and how does it compare to all of the formulations that we have. And these are some of the figures that we got out. The main takeaway is that the creep length is less within every system, which we thought was substantial. So just to give you another indication of where FEV top coats are good in corrosion is if you look at any standard test for the 1294-4, it's going to pass. So it's going to pass all the duration hours it need for aging, for cathodic disembodiment, for seawater immersion. So any of these tests you're going to put it through, it's going to pass the most rigorous, the harshest environments. We're confident on that. And what's pretty cool is that another area that we're looking at is the electrochemical impedance spectroscopy. So that's one of the aspects that we're pretty excited about, and within this testing, essentially you're going to test your full formulation, and it gives you a way to rapidly test. Of course, we want to age it because aging is one of the benefits of the Lumephon system. So what we did was we took this electrolyte, we put it on top of the coating, put it on a panel, and we went through and tested it. So we went through all of these surface treatment, non-destructive. We wanted to monitor the corrosion and the water absorption. And to give you a diagram of just a small body diagram of what's happening is you have your electrolyte on top of your coating that's held on like a glass beaker, and we have a photo in the next one, where you have your corrosion reaction you're trying to create, and then you have your metal underbody surface. So this is what it looked like, and those are the materials and the frequencies that we went through for this testing, and I'll show you some of the boat plots and the Nyquist plots next and extrapolate some of that data to give you an indication of how these perform versus what you're accustomed to with polysiloxane or polyurethane when you're coating your systems. So within that, we have the two plots which are for the EIS testing that you'll pull out a Bode plot or you pull out a Nyquist plot. The Bode plot is you just take a point in time and you can compare like what that frequency is for the impedance. So it just gives you out the Hertz number. And then the Nyquist plot, essentially you're looking at that resistance. And a perfect corrosion resistance insulator on a Nyquist plot is going to be straight up and down. That's what you want. You want that infinity, that the mathematics, if we're going back to the whole textbooks, that's what you're looking for. So anything that shifts on that graph to look more like a straight up and down line to the left, that's what you want to see. And that's what you want to see over a long time and get out of those Nyquist plots. So that's kind of how to interpret those as you're looking through them. And so we looked at these for the FEV, which is the lumiflon, the polysiloxanes, and the polyurethanes. And initially starting out, all of them are pretty good. Anything 10 to the 8th ohms per centimeter squared resistance is a very good insulator to prevent corrosion. But it's not necessarily the start. Like, the start's great, every car off the lot looks like it's great, the paint's great, drives well. It's really, once you go take it out in the real world, how does that perform? And that's what we really want to look at. And so if you continue to soak this, you can then pull out, okay, well, what about after 50 weeks of electrolyte soak? And yes, EIS is rapid, but for this, we want let's bring it out into some testing and put it in a harsh environment. Let's pull it out and see where the Nyquist plot does after 50 weeks of soaking it. And that's where you start to see the performance difference of a lumiflon and FEV based, still maintaining that graph of up and down as much as possible compared to if you're looking at a polyurethane or a polysiloxane. So these are the figures that we have measured at the impedance of 0.1 hertz. And if you look at the different soak cycles for 50 weeks and 120 weeks, and you see a pretty similarity in the initial, but after you start to spend time, you definitely see lumiflon maintaining its performance, and you see the polysiloxane and the polyurethane trending down over time, and having a reduction in their corrosion potential resistance. This is that last one visualized, just to make it a little bit easier on the eyes to see, and that's what we're seeing within our electroimpedance testing to say, hey, yes, we are confident that this is going to help corrosion when you're looking at painting your surfaces with this technology. So just to highlight some of the takeaways, we looked at the EIS testing. It's a short-term test method, meaning it takes less than 1,000 hours, so we can get quick information back, and you can get actual corrosion results that determine initial impedance, the water uptake, and the corrosion resistance of coated steel. And this one, I know we talked about the rapid, and I want to show you a little bit about like some of the other technology we've used this, because corrosion isn't necessarily only for bridges, but you can do it rapidly. And we did it in some powder coatings that we were testing. We wanted to see performance characteristics of how it went through powder testing. So this is just to prove that yes, you can do the method. And so we looked at a faster screw and a slower screw on a powder coating, which isn't necessarily used for bridges, but you can pull out those measurements pretty quickly. So you can get it within 168 hours, which is less than a week on terms of that timing. So you're not waiting 10,000 hours or 20,000 hours to put this in an accelerated weathering test that might be expected at some of the other standards. So that's where we believe in corrosion, and to kind of transition of, yes, these products are being used now, and people are already taking advantage of them within the US. And some of the case studies is there's different specifications that you can look at. If you're looking at using these for your state or your municipality, there's different specifications to kind of draw from. It's not reinventing the wheel. So we have the AMP Paint 47 standard, as well as we have a couple of different standards that are coming out on some bridges. So I don't know if anyone's familiar with the Iowa DOT I-74. They have their special spec that they've written that they can take advantage of this system. And it's going to be a system where you're only looking at, if you're looking at a lumiflon, it's going to use in any traditional 3-coat system. So you have your zinc-rich primer, you have your epoxy mid-layer, and then you have your top coat, that's where you're going to want to use our product and use that within the paint formulation. So they will submit that 3-coat system, and that's where you really get the advantage of it. So that's, it's already in use on roadway bridges in the US today. It's extensively used in Japan, as talked through, and have examples. And you ask, well, that's great, you're selling me all these benefits. But what about the cost? Because everything definitely has a cost, and I'll be honest, yes, it is an expensive product. There's no way around it. It's hard to manufacture, so it's hard to sell that profitably for a company. So that is definitely a hurdle rate when you're looking at different projects. And we wouldn't recommend it on every product, every bridge, or every application. But the one thing to keep in mind is, what are the important bridges that you're painting that you don't want to have downtime? You don't want to have maintenance time. If you look at it and per paint, yeah, your total cost per square meter, yes, you are looking at a more expensive product, even 2 or 3 times more expensive, depending on what you're able to procure polyurethane at right now with where materials have gone. The part to think about is a polyurethane will get you 15, maybe 20 years if you stretch it out. We gave it 18 within this simple estimate, whereas a FEVE or Lumiflon system will get you 30 to 60 years. So you're looking at 15 more years of a coating. So the fair comparison that we feel is compare it per meter squared per year. And that's where you really will start to see that benefit in terms of the weatherability, the corrosion resistance, that you don't have to bring your bridge out of commission, you don't have to repaint it, you don't have to surface prep, you don't have to worry about all the things that you might if you have to continually repaint these bridges. And that's just for the top coat. So that doesn't include your primer and your epoxy mid layer and your top layer. And you can use the same epoxy and the same primer, the zinc primer that you're using, or maybe some modified one depending on the recommendations that you would switch to from the polyurethane to the FEV technology. But that's a pretty substantial savings when you're thinking about what the cost index per area per year is for these materials. And like I said earlier, just to get through some case studies, and then I'll flip through some photos just to give you guys examples. But this is a bridge in Japan, and we tracked it over 30 years just to look at the gloss and the color retention. It actually was double coated, so it was coated with FEVE and a polyurethane, and then after like 15 years, they just coated it all with an FEVE or Lumiflon system. So that's where you can see the benefit. So you can just look at the gloss retention over time, where you can see a delta E of 2.3 and 3.4. So that's a pretty substantial retention of where you're going to see visually that bridge over time. And just to give you some projects that are going on within the US right now, the Sunshine Skyway Bridge in Lower Tampa Bay, Florida is being painted right now with a top coat of Lumiflon. So that's a pretty substantial project in a pretty harsh environment. And it's the steel portion of the bridge. So those are things where when you have these harsh environments, when you have to paint your steel portion, consider looking at what the life cycle cost would be for using a Lumiflon technology. And then another example in California is a little bit unique. So they're using a blended material within a water-based, because they have certain VOCs and they want to move everything into a water formulation. They're getting performance that they have in it's open source on a green and a blue. So they have a couple of different projects they're painting right now with a water-based, where they're seeing the advantage of moving to a Lumiflon-based technology. This one's a blend, so it's an acrylic and a Lumiflon. So they painted the Cold Canyon Spring Bridge, as well as they've been working on the Bay Shore Viaduct. So they've just finished painting those, as well as they're continuing to look at more and more bridges in California that they're looking at. And just to give you some other examples, there's Des Moines, Iowa, the I-23 pedestrian bridges, a couple Skydance bridges, some iconic ones that you might be aware of, see very visually appealing. It's in that area where you want a high performance, people are going to see it, it's got value in that. So these are some of the pretty images like we like to show off, and we care because we believe in the technology, and we want the states to save money on their preservation costs, and this is an opportunity to consider it that we hope you look into. So with that, does anyone have any questions?
So a quick question. I assume you have the AMA 2605 data for this as well?
Correct. AMA 2605 for architectural, correct.
Okay.
And AMA 2605 is more architectural, but that can be done powder, liquid. Happy to discuss what you're looking for there. But yeah, the paint manufacturers will warranty 20 plus years, 25 plus years, depending where you sit on the sun, the equator line.
Right, okay.
Good.
I was curious for the formulation you're doing for Caltrans for the, the water base, the VOC, do you expect that has an impact on the expected life?
Yes, so you are not going to get the same performance. So the best performance is going to be solvent. You're not going to get the same performance if you do go water, but you are going to get better performance if you're forced into just water, or you want to just do water. You're going to get better performance if formulated well than anything else. But if you're looking for the top end echelon, go solvent, go Lumiflon based.
Do you have any idea what the relative scale would be?
They own a lot of the testing, so we make the resin, so they own a lot of the testing on the relative performance of what they feel comfortable with.
Yeah.
So we don't own that information that they've developed on their formula.
I was just wondering, I've heard, and I'm not real knowledgeable about it, but looming legislation on isocyanates, is that going to affect the FEVs the same as urethanes?
So right now, the most standard way of cross-linking a Lumiflon system is with an isocyanate. We are working on how to get the same performance out of other materials right now. But yes, that is the standard method of working on it. And if it will affect some of the outcomes, we're working on that within our labs of finding better formulations to meet what's coming on the line.
All right, thanks, Bill.
Thank you.
Appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.